In this video, I'm going to show you how to use the fixed effects regression program. I'm going to come down to the button and click on it. When I do, the full instruction set for how to use the program appears in the description box. I'm not going to go through that because I'm going to be summarizing the essence of it here. We're going to be inputting information into the input values box, but because this uses raw data, the first thing I need to do is to go get the data. So I'm going to click on Choose File. This is on the C drive in the folder RET. And I'm going to find the data file I'm going to use, fixed reg 1. I'll open that. This box then shows me the variables that are in the data file, and this is very important for me to have as reference because I'm going to have to enter variable names over here. R is case sensitive, so I have to be very careful to respect the capitalization in it. Up here, I'm going to put the full folder address as well as the file name so it can find it. And then I'm ready to enter the information here. So fixed effects regression is widely used in some disciplines such as sociology and economics, but it's used less often in domains like public health and psychology. I discussed the technique in my book. It has both strengths and weaknesses. You can get all the details for it in the book. When you use the program, you have to have data in long format instead of wide format. Some of you may be familiar with the two, but let me briefly review the difference between wide format and long format and talk about how you would put your data into long format. So I'll show you using an SPSS data file. This is a classic setup that is in wide format. I've listed just 4 individuals here in the data that we're going to analyze. I have many more than that. Let's suppose I had a RET where I had a baseline assessment, a mid-treatment assessment, a post-test assessment, one at 6 months and one at 12 months. And I measured mediators as well as covariates and outcomes at each one of those 5 time periods. In this wide setup, here's the mediator 1 measured at time 1, mediator 1 measured at time 2, mediator 1 measured at time 3, 4, and 5, and then I have the outcome measured at time 1, 2, 3, 4, and 5, and in this case biological sex. For each individual, they occur in one row, and then I have all the variables that I assessed as columns. That's kind of the classic setup. In long format, if I have 5 time points, each individual will have 5 rows. And so I've indicated here for the first individual the ID number, and then for the second individual the ID number. And then I have the 5 time points for each individual. So this is the baseline, this is the mid-treatment, post-test, 6 months and 12 months. And then this is the score on M1 at each of the 5 time points, for Y, the outcome on each of the 5 time points. And then the person's gender is the same across those 5 time points because their gender doesn't change over time. So this is set up in long format, and this is how we have to have the data structured. I give right above the video link for this program a PDF called data file that explains how to convert data from wide format to long format. So you can look at that and see how to make that conversion simply. The essence of fixed effects regression is that it's going to look at and essentially regress Y onto the predictors, in this case the mediator, within individuals across time. And it's going to remove all the effects of between individual variability. That is going to control for any individual differences across the variables. The way it's going to do that in principle is it creates a dummy variable for each individual. So for example, D1 is a dummy variable, and if an observation comes from the first individual, it gets a 1, otherwise it gets a 0. And here's a dummy variable for the second individual. If the observation is from the second individual, they get a 1, otherwise they get a 0, and so on through every single individual. So if I had 100 individuals, I would have 99 dummy variables that I would create. And when I do the analysis, I would regress y onto M1 and all of the dummy variables as well. And by including those dummy variables, by covariating them out, I essentially control for all the individual differences. Now, the actual analytic strategy that's used by the program in R does not create the dummy variables. It does not use this technique, but it does so in spirit, and it effectively removes all the individual difference variability from it. Let me go ahead and minimize these. Now, the reason this is powerful and very important is because let's suppose I want to look at the causal impact of a mediator on an outcome. What I assume is that the main reason these guys are associated is because the mediator has a causal impact on outcome. But suppose there are common causes out there that also influence both of these. For example, suppose gender influences both the mediator and the outcome, and SES influences both the mediator and the outcome. As I discuss in my book, this can create bias if we infer the causal coefficient from the degree of association between these, because there are actually 3 sources of the association between the mediator and the outcome. First, there's the causal influence of the mediator on the outcome. Then another reason they're correlated is because gender influences both of them. It's a common cause. And a third reason they're correlated is because SES influences both of them. So that if I just use the association between these two variables as an index of the strength of this causal relationship, I will overestimate that relationship. What we need to do is we need to control for gender and SES, and then once we've controlled for those, we get a better estimate of this causal impact by looking at the association. Advantage of fixed effects regression analysis: it controls for every possible between individual variable that could exist. By covariating out all those individual differences, I'm controlling for gender, for SES, for ethnicity, for age, for everything that is a between individual source of variability. And that's a very, very powerful approach for then estimating the causal effect of the mediator on the outcome. So the first thing I have to do is put in the ID variable here that identifies different individuals. And this is very important because it's going to flag this variable in order to control for all the individual difference variables. Then I have to put in the equation that I'm interested in estimating. And in this case, I might predict y from 2 mediators, M1 plus M2. Okay, and so this is basically going to do the regression of y on M1 and M2 within individuals. Okay, I'll explain how I use these other variables in a little bit. So I'm going to hit register input. The syntax is generated here. I'm going to copy that to the clipboard. I'm going to open it up in R. And then I'm going to paste the syntax here. R will execute the syntax as it's pasted, and we'll see the results accordingly. Okay, the output appears in blue, and the syntax appears in red. Now, I report 2 forms of analysis. First is the traditional fixed effects panel analysis, and then the second is the same analysis but using a robust estimator or robust standard error. I prefer the robust standard error estimates, and it's a little technical, and I explain it all in my book, but the output is pretty straightforward. This indicates that I have 80 individuals in this with 5 observations per individual for a total number of observations of 400. And here are the results in terms of the coefficients, the standard errors, the t-values, and the p-values. It also gives an adjusted r-squared and an overall omnibus test. I'm going to focus instead on the robust analysis. Here I get my two estimates. The estimate of the effect of M1 on Y is 2.03. That has a standard error of 0.137, and that's statistically significant. The estimated effect for M2 is minus 0.09. It's holding M1 constant. In this case, for every 1 unit that M1 increases, Y is predicted to increase by 2.03 units, and that's statistically significant. And again, this is controlling for all of the between individual variability. So that's the essence of this analysis. And I'm going to show you another application of it. This model has assumed that the effect of M1 on Y and M2 on Y is the same for everybody. We might think there are gender differences in the effect of mediator 1 on Y. And so I want to allow for the fact that the coefficient for M1 might be stronger in males than it is in females. Now I can't just simply add gender into the mix here because I've removed all the between individual variability. So what I do is I created product terms here, and this is a product term between M1 and the dummy variable where males get 1 and females get 0. And then another product term where I multiplied M1 times a dummy variable where females get 1 and males get 0. So what I'm going to do is I'm going to add to this equation that product term. And as you know from my book, the product term gets at an interaction effect. Now normally when we do interaction analysis and we put in a product term, we make sure that the individual components of that product term are in the equation. And M1 is in this equation, but D female is not. And it turns out I don't need to add D female because by controlling for between individual differences, I've effectively removed it and controlled for it. So all I need to do in this case is to put in the product term. Again, I discussed the details in my book. So this then allows for the effect of M1 on Y to vary as a function of gender. The key here is that M1, the time varying variable, in combination with the between individual variable of biological sex. So I'm going to register the input for that. I'm going to copy it to the clipboard. I'm going to open up R. And I'm going to hit Control V. I get the same output, but now I have M1, M2, and the product term. Here's the effect of M1 on Y, but because it's part of the product term, this is the effect of M1 on Y when D female equals 0. So this is the effect of the mediator on the outcome within individuals for males. All right? For every 1 unit that M1 goes up, Y goes up 3 units. The product term is the difference between this coefficient and the coefficient for females. So I can tell from the product term, because it's statistically significant, that females have a statistically significant different slope or coefficient than males do, and that it's going to be about 2 units less than that for males. And I can show you that if I close this out, go back to the model, and change this to reflect males, M1 times D male. That is, I flip the dummy variable. I'm going to register the input to update it. I'll copy that to the clipboard. I'll open R. I'll paste it. And here's the result. The product term is exactly the same except it's flipped its sign. Significance is the same and everything else. And here's the coefficient for the effect of M1 on Y when D male equals 0, which is females. And that coefficient is 0.979. So you can incorporate group differences in looking at the effects of a mediator on an outcome by the use of product terms. And it's a very useful way of exploring causal relationship between a mediator and an outcome while controlling for many, many different confounds. Okay, I'm going to close this. And I'm going to show you another application of it that I think is very interesting. And again, I discussed this in my book. For this one, I'm going to use a different data file. I'm going to use fixreg2. I'll go and get that data file. Right there. And these are the variables that are in the data file. I'll be adjusting the input in a second. Now let me open up an SPSS file that will help me explain what I'm going to do here. So this is in long format, and let's suppose that I have 5 time points. I'm going to analyze decay functions, and let's suppose that I have an RET where I gave people a treatment, and then I measured them at the post-test, and then I did a follow-up 3 months later, a follow-up 6 months later, a follow-up 9 months later, and a follow-up 12 months later. That is, there are 3-month increments between these guys. I discuss in my book if you have unequal time intervals, that's easy to accommodate. This is the person's outcome score at each time point. And let's suppose my outcome is anxiety. I have a treatment that is trying to impact anxiety. And let's suppose as scores go up, the people are more and more anxious. So decay would be indicated by the score going up over time. In this case, this first individual is decaying over time. If I want to analyze decay curves and see what the decay is as a function of 3-month intervals, then what I would do is I would put in the ID here, and I would predict Y from time. And then this is going to examine how anxiety changes as a function of time, where time is in 3-month increments starting with the post-test and going out through 1 full year. So I'm going to register that input. The syntax gets updated. I'm going to copy it to the clipboard. I'm going to open up R, and I'm going to paste it. So this is the fixed regression effects model, and here I see that using the robust estimator that for every 1 unit that time goes up, and in this case the unit is in 3 months, anxiety increases by 2 units, and that's statistically significant. And so this tells me the decay curve. For every 3 months that passes, the anxiety is going to decay by 2 units, assuming a linear function. So this is a very interesting application that you can use. It's like growth curve modeling, but it's coming at it from a slightly different angle using the fixed effects regression modeling instead of the more traditional random effects modeling that growth curve models use. Suppose I am comparing 2 treatments, and I have treatment A and treatment B, and I might think that the decay curve is different for treatment A than it is for treatment B. And half my individuals take treatment A and the other half get treatment B. Well, I can test if these decay curves differ by bringing in product terms, just like we did before. So I'm going to close this, and I'm going to come back up here. And again, here's a dummy variable where if they had treatment A, they're a 1, otherwise they're a 0. And this is a dummy variable where if they had treatment B, they get a 1, otherwise they get a 0. And here are product terms between the time variable, time 3m, and each of those dummy variables. If I add the product term for treat A, that's going to allow for the effect of time to vary as a function of whether or not you're in treatment A versus the reference group treatment B. And again, I don't need to put in the component part of the between subject variable, i.e. treat A, because that's already been removed when I took out the between individual variability. So I'm going to register the input. I'm going to copy that to the clipboard. I'm going to open up R, and I'm going to paste that. And here are my results. It turns out I do get a significant product term, that the effect in treatment B, the decay curve in treatment B, is significantly different than the decay curve in treatment A. This is the estimated effect of time on the outcome when treat A equals 0, or this is it for treatment B. So in treatment B, for every 3 months, anxiety decays by about 1 unit. The product term coefficient tells me that the coefficient for treatment A is going to be about 2 units higher than that. It's going to be close to 3. And I can see that if I go back, and instead of treatment A here, I use treatment B. I register the input. I copy it to the clipboard. Open up R, paste it, and there's the effect for the effect of time on the outcome when treat B equals 0, which is treat A. Okay, so A has a much higher decay rate than treatment B. And in fact, there's about a 2 unit difference between the decay rates. So you can look at differences in decay rates as a function of individual difference variables such as treatment. And there's a lot of really interesting applications you can use for this technique. I discuss them in detail in my book and also go over the whole product term analysis thing, so you can take a look there. Okay? All right, that's it. Thanks a lot.